today, just extending the stuff we've already done, right? We talked about how to simplify square roots. Remember what our strategy was? We wanted to find the biggest perfect square factor of the radicand, and then break the square root up into two parts. Or if it's a big number, we just deferred to couples go out, singles stay in. So what are we going to do if it's a cube root? Triples go out, everybody else stays in, right? Triples go out, everybody else stays in. So singles and couples stay in. What if it's fourth root? What would we do? Quadruples go out, and then everything else, singles, couples, and triples stay in, right? So it would be, you just extend the rule, but everything works the same. So we would just take this big number, 21,600, and just like before, we're going to make a factor tree out of it. So let's do that. Okay, what do we get here? 21,600. What could we do here?
I feel like 125 might do it.
Okay, but we've got two zeros at the end, so what's an obvious number that goes in? 100, there you go. Okay, so we can break this down to 216 and 100, right? Okay, 100 breaks down to 10 and 10, right? And then 10 and 10 breaks down to, okay. And then those are prime, right? So we can stop there. What about the 216? Okay. Okay. Let's see if you guys can use your divisibility rules. 3 works. Is there a bigger one I could take out? 9. Good. 2 plus 1 plus 6 is 9, which is divisible by 9. So 9 would be a bigger number we could take out. So 9, and what was it? 9 and 24. Okay, 24 breaks up into 3 and 8. And so that's going to give us 3. And then what's 8 going to be if we'll just skip a step? 2, 2, 2. And 9, of course, breaks down into 3 and 3. So if we just organize this then, smallest factor we see is a 2. How many 2's do we have? 5, okay? So we've got square root of 2 times 2 times 2 times 2 times 2. Next one is 3. How many 3's do we get? 3. And then we get, what's the next one when we're into 5's? How many 5's? 2, okay? All right, so do we get triples here? We get triple 2's, but then after that, we only get one triple 2, and then after that, we don't quite have enough for another triple, right? So we get some stragglers, but not enough. And then we get triple 3's. So what is our answer then? Okay, good. So outside, we're getting 2 times 3, which is going to give us a 6. Inside, got all the rest, right? Okay, so inside we've got 2 times 2 times 5 times 5. So we could simplify this to 6 outside. Inside we'd get 100. Yeah. Okay, everybody good? Make sense? Okay, same idea, no big deal. You guys got this. Okay, so here's the part the slightly heavier lifting for today. I want to show you guys an awesome trick. This is not in the textbook. In fact, I've never seen this in a textbook, but this is one you really want to learn because it makes this stuff so easy. When a radicand is a power, so we've got a power of a variable inside a radical, right? So the radicand, what's inside the radical, is a power function. It's a variable to a power. Here's the trick. So write the expression using rational exponents. So is that first step, we've done a lot of this. Does that make sense? Give me thumbs on that the cube root of x to the 11 is the same thing as x to the 11 thirds. We're all good with that? So write it as a rational exponent. Then here's the trick, awesome trick. Write the exponent as a mixed number. So 11/3 as a mixed number. Everybody agree 3 goes into 11 how many times? 3 with how many remaining? 2. So we get the mixed number 3 2/3, right? Think what a mixed number means. When we say 3 2/3, and I think we talked about this earlier in the year, this is one of the many reasons that we abandon mixed numbers after middle school, right? It doesn't look right. 3 2/3, really, it looks like 3 times 2/3, but what is it really? 3 plus 2/3, right? So if you think about that as x to the 3 plus 2/3, well, look what we can do. We can split up, we can kind of work backwards with our property of exponents that says this. X to the m plus n is just x to the m times x to the n, isn't it? When we multiply like bases, we add the exponents. So we can split that into two separate powers, x cubed and x to the 2/3, right? Well, the x cubed, there's no radical there, right? That's no longer a fractional exponent, but the x to the 2/3, we'll just flip that back and rewrite that as a radical. And we did it, right? We got as much outside the radical as we could. Now, at your level, do you need to explicitly write out all those steps? Probably not. Probably you just you write it as uh, a fractional exponent, and then in your head you're just turning that into a mixed number, and you're taking the integer part of the mixed number goes out front, the fractional part becomes the radical part. Okay, make sense? Give me thumbs on that. Does that all make sense what we're doing? Okay, so let's try this again. The power, the outside part is the integer part of the power of the mixed number, and the inside part comes from the fraction part of the mixed number. Okay. Okay, so I mean, really, really quickly, go. This ought to be like 30 seconds. Go to the board and do this one.
So it's like x2.
Evie, you're.
You started the recording?
I did. Thank you. Okay, here we go. Here we go. So real quick, we would start off. We would write this as a mixed number, right? So x to the 8/3 is the same as what? X to the 2. Oops. Let's make this to the 2 and 2, and there's an invisible plus sign there, right? 2 2/3, right? So then that becomes, I get an x squared outside, inside, I get an x squared because of the numerator, right? The denominator of the fraction, of course, is just, that's the type of root that we have, which is a cube root. Okay, no big deal. All right, what do we do in the event that it's a little more complicated? What if we've got a lot of stuff going on at the same time? We don't just have a single variable. Maybe we have multiple variables and a number. What do you think we're going to do for a problem like this? Yeah, we're going to put them individually, right? We'll just break this into a bunch of parts. That's it. How many parts are there? Well, there's 4. We've got the number part. We have to simplify the 4th root of 288. And then we've got 3 different variables, and we'll just do those individually, right? So what's that look like then? If we break that into parts, here it is. We got the 4th root of 288 times x to the 7/4, right? Y to the 1/4 times z to the 18/4, and we just deal with them individually. Well, 288, I mean, if we make, I'm going to skip, I'm going to skip the factor tree. You guys can all do a factor tree for 288, but just pretend we did. If we did a factor tree, we get 1, 2, 3, 4, 5, 6, 7. We get those 7 prime factors from 288, right? What's our rule for a 4th root? You guys already told me that's going to be quadruples go out, everything else stays in. So it looks like we've got 1 quadruple and a bunch of other stuff, right? So the quadruple, we have 4 2's, right? So the quadruple 2 gives us a 2 outside, just a single 2, right? You get 1 2 for a quadruple. And then inside, we're stuck with a single 2 and a couple 3. So that gives us 2 times 3 times 3 is 18. So the number part's no big deal. We get a 2 outside and 18 inside. What about the x part? X to the 7/4. Well, as a mixed number, 7/4 is what? 1 and 3/4. Okay, so for the x's, we're going to get an x to the 1 outside. And then inside, we had an x to the 3/4, which means we're going to have a cube root of x inside, right? Give me thumbs. We good with that? Okay, what about y to the 1/4? Well, as a mixed number, y to the 1/4 is just 1/4. So that we can't do anything with. We're stuck with a y to the 1 or just a y inside. Nothing happened there. Okay, what about z to the 18/4? Now, here's where you got to be a little bit careful, so pay close attention. Here's where people can sometimes make a mistake. 18/4 as a mixed number is 4 and 2/4, right? So we're going to get an x to the, or sorry, a z to the 4th outside. Now, what about the fractional part? We've got z to the 2/4. Do we want to flip that to a 1/2? You're right, we don't. How come we don't want to change that to a 1/2? Good, because we're stuck with a 4th root. So we don't want to reduce any fractions when we're doing this trick. And we have multiple variables. Does that make sense? Because we got to keep the same root the whole time. We can't have a mixture of different roots. It's a 4th root that we're simplifying. So we keep the denominator of 4, and inside we get a z squared. Make sense? Okay, so no big deal. Just break it into individual parts. Don't reduce fractions. Keep the denominator the same for all the parts, and that's that. Okay, so go try one of these on the board. Okay, let's take a quick look. Looks like everybody got this. So what'd you find for 243? Good. So it equaled 243 equaled just 5 3's, didn't it? It's just 3 to the 5th. So that gives us a quadruple 3. I think I'm changing my colors around though. It gave us a quadruple 3, and then I had one single, right? And then how about x to the 4th root of x to the 9th? What's that give us? X to the 9/4. As a mixed number, that's going to be x to the, say it again, 2 and 1/4. Okay, 2 and 1/4. So our answer then, we've got some outside stuff and some inside stuff. What's my outside stuff? Okay, so I get a 3 for the number part. I get a 3 outside, and then inside. But just do the number first. 3. Okay, how about the x's? What do I get outside? Inside. And how about the y's? Just leave a y because we get y to the 1/4. There is no integer part of that mixed number, right? So we're stuck with a y inside. So that's what everybody got, I think, right? Okay, last one, and I'll turn you loose to work on this. Okay, what would we do there? Take a look at that. Think about that for a second. What would I do? Okay, what about the top and the bottom? Solve them individually? Okay, I could. Could. Okay, yes. Okay, now if we deal with these individually, it's going to work, but you're buying yourself a lot of extra work. Notice that because these are both 4th roots, there's a trick here that saves us a lot of time. What's the property of radicals that we're using here? If I have a 4th root of A over a 4th root of B, what can I do with that? You guys are used to starting with a fourth root of a fraction and splitting the radical, but we can reverse that, right? So what do you think?
The fourth root of a over.
Yeah, we just combine those. We unsplit them, right? We turn those into 1/4 root of a fraction. It's already split, so we reverse that process. And we get the fourth root of the big fraction a over b. The advantage of that is maybe we can simplify that fraction before we deal with the radicals, right? Okay, give me thumbs on that. Does that make sense? Why that would be a good idea here? Okay, so if we do that, that's going to give us the fourth root of 96 a to the 10th b to the 4th over 3 a squared b to the 4th. Okay, how would we've got this big expression inside the radical, how would we approach simplifying that? What would you organizationally, what would you do? Split it. Okay, so good. So we split it into parts. We got the fraction of the numbers. We could deal with that, right? So 96 over 3, what's that become? 32. Okay, so we get a 32. How about the a to the 10th over a squared? What does that become? A to the 8th. And how about b to the 4th over b to the 4th? Oh, nice. Those cancel. So they're completely out of the picture. This looks a lot better, doesn't it? Right? Now we can just turn this into, we can break this into two much, much easier parts. So I've got the fourth root of 32 times the fourth root of a to the 8th. Okay, well, how does 32, if I make a factor tree out of 32, can anybody tell me how's that going to work out?
2, 2. Wait, how many times? 4.
Yeah, 32 is 2 to what power? The 5th, exactly. So I'm just going to cheat. And we just get that, right? What's our rule here? Quadruples go out, everything else stays in, right? So what do we get here then? I get one quadruple and I get one single left over. How about the fourth root of a to the 8? What's that going to become? A squared, right? That whole thing, this is just going to become, I'm going to get an a to the 8/4, which is just an a squared, right? So all the variable comes out. There is no fraction part. So what do we end up with then? Okay, so we get, what goes out? 2. And what's left inside? Just a 2. Yeah, that's it, right? All we had left inside was just this 1, 2. And that's it. Okay, make sense? All right, I'm done. You may work. Put this up on the notes. Assignment's up.